Hello, everyone. Welcome back. This is the third lecture for Module 4. So let's get started. We still have some nomenclature to go through with different types of molecules. Okay, so let's start with hydrated compounds. Hydrates are ionic compounds that contain a specific number of water molecules. And that specific number is associated with each molecular or each formula unit of the particular salts. So for example, my base ionic compound would be magnesium sulfate. And when that's hydrated, it actually recrystallizes into its lattice. But for every one formula unit, I have a specific number of water, which is 7, attached and incorporated into the crystal. So this is called Epsom salts, if you've ever heard of that before. And this would be called magnesium sulfate, which is the name of that salt, heptahydrate. Hepta means 7, and hydrate means water. And I think everybody knows that intuitively. If I'm hydrating, I'm drinking water. So this guy, I would first, in order to name this hydrate, I would first name the salt. Cobalt is a transition metal, so I'm going to have to use a Roman numeral. I go by the fact that Cl is -1, and I have 2 -1s, so my negative actually adds up to -2. That gives me the charge on cobalt as a +2. So the name of this salt by itself is cobalt 2 chloride. And then 6 would be a prefix hexa, like a hexagon. And then, so this gives me the number of waters. And then hydrate is indicating that I do have water molecules in the crystal structure. So the common hydrate prefixes are mono equals 1, di equals 2, tri equals 3, tetra equals 4, penta equals 5, hexa equals 6, hepta equals 7, octa equals 8. These are pretty standard prefixes that you've probably already been exposed to. This one might be new. And I can actually have a half of a water associated with a particular formula unit. So basically 2 formula units per 1 water. But because I'm looking at the number of waters per formula unit, I would get this hemi. So here's some other examples. Here's an example where I use that hemi prefix. This is calcium sulfate hemihydrate. So again, this prefix is going to be the number of waters that are in that crystal structure. So I name the salt, then I have my prefix followed by the word hydrate. This would be barium chloride, hexahydrate. This would be copper sulfate, hexahydrate. This dot is also an indication that this is a hydrated compound. So I have the salt, which is just the ionic compound, and then I have the dot, which is always indicated in these hydrated compounds, and then I have the number of water molecules that are in that crystal structure. So there's a couple of components to these. Now, these hydrates can be the water that's in the hydrate can be driven off by heating. So I can actually turn the hydrate into the anhydrous molecule, or the anhydrous ionic compound, by heating it. But you'll notice that when I look at the hydrate, I have different physical properties. For example, this cobalt 2 chloride hexahydrate is this red color. And when I drive off the water, so when I make it anhydrous, which means without water, this would be the anhydrous salt because the water's not there. It's this beautiful purple color. Purple is my favorite color, so I happen to really like this guy. But there will be some formulas where you can actually use the ratio of the water molecules to the mass of the salt, and you can figure out how many water molecules are actually hydrated in these different salts. So pay attention for that. I think there's a couple of those in Mastering Chemistry. Now, that's the end of the ionic section. Now we're going to turn our attention to molecular compounds. Remember, molecular compounds are covalently bonded nonmetals, and I have that fundamental molecule as my unit. The formula for any molecular compound cannot be readily determined from its constituent elements, because the same combination of elements can form many different molecular compounds, and each of those compounds can have a different formula. For example, if I combine nitrogen and oxygen, I can get a whole host of unique molecular compounds. I could have NO, NO2, N2O, N2O3, N2O4, N2O5. Here, I have a 1-to-1 ratio, right? 1 nitrogen atom, 1 oxygen atom. Obviously, here I have 1 nitrogen atom, 2 oxygen atoms. So nitrogen and oxygen can combine and bond in multiple different ways, which means that I can't just look at them and predict that this is going to happen like I can with an ionic compound, knowing the charges that I can have on those ions. So remember the basics. Molecular compounds are composed of 2 or more nonmetals. And what I'm going to write first is the name of the element with the smallest group number. So anything to the right on the periodic table, right? The smallest group number. If 2 elements are in the same group, then the element with the greatest row number is written first. I'm going to use prefixes for both the elements in my molecule, because that's going to indicate the number of atoms of that type of element that's present. So here's my scheme. I would have a prefix, which is the number of atom 1, right? And this is going to be the lowest group number, or if they're tied, the highest row number, right? And then this is atom 2. And then that gets changed to an IDE. I'm going to use prefixes that are exactly the same as those used in naming hydrates. Here I've gone up to 9 and 10 as well. Here's a convention though. If there's only 1 atom in the first element, I'm going to omit the prefix mono. So I wouldn't say mono carbon dioxide. if I have CO2, right? I wouldn't do monocarbon. It would just be carbon dioxide. So here are the rules. Do not use the prefix mono when naming the first element. So this would be monosulfur trioxide if I used the prefixes, but I'm not going to do that. So basically this is going to be called sulfur trioxide. When prefixes end with a vowel, either an O or an A, I'm going to modify the words that come together when the element that comes after it begins with a vowel. So this is tetraphosphorus decaoxide. What I'm going to do is get rid of that, and really it's going to be decoxide. All right. Acids. Those are another type of molecular compounds. Acids can be recognized because they usually are composed of hydrogen, which is written first in their formula. And then I could have either another nonmetal or a polyatomic after the hydrogen. Acids are molecular compounds, so they're all covalently bonded, that release hydrogen ions, which are H pluses. And this is important when they're dissolved in water. So you might have seen HCl or H2SO4 or H2CO3. With the hydrogens being in the front, they're always going to be indicating typically that they are acidic compounds. Now, we're going to talk about acids a lot later in terms of their reactions, and you'll get into a really intense discussion of acids when you take Chem 2. Let's go over a little bit of the properties of acids. They're sour. I don't recommend that you ingest acids, but if you think of lemons and you think of a lemon juice, which is very sour, that's due to the citric acid in the fruit. They can dissolve metals. Some metals are very reactive to acids, and others are not very reactive. Now, this is gold, silver, and platinum. Some of you guys may recognize that as metals that are commonly used in jewelry. You know, if you're going to put something in your ear or wear it around your neck or on your finger, you don't want that metal to be very reactive. So it's no accident that jewelry metals are actually very unreactive metals. The formulas are going to start with H, like HCl or H2SO4. HCl, for example, is a molecular compound because it has two nonmetals. When it's dissolved in water, it's going to dissociate or ionize to form H plus and Cl minus. The aqueous, which is this symbol here, just means it's dissolved in water. So here you can see these bubbles are actually caused because hydrogen gas is released when the acid is reacting with the zinc metal. There are two types of acids that we're going to worry about naming. There's binary acids. I only have two elements. This would be HCl. I have a hydrogen, I have a chlorine, two elements. And then there's oxyacids. Well, where have we seen that term or that term before? Anything that contains oxygen. So this is going to be like H2SO4 And basically, this is due when I have polyatomic ions that are pronated that have the hydrogens. So binaries have an H plus cation and a nonmetal anion. And then oxyacids have an H plus cation and my polyatomic anion. So 2 different naming systems. When I name those binary acids, so again, just 2 elements, I always start with hydro as a prefix. Then I have the nonmetal base name, that root name, and then I'm going to add this suffix, which is IC. And then I have acid. So I have hydro, base name of nonmetal plus ic, and then the word acid. So this is the system for binary acids. So here we go. If I'm going to name HBr, right, I'm going to use hydro. The nonmetal base name, well, this is from bromine. So the nonmetal would be bromo. And then the suffix ic, and then the word acid. So this would be called hydrobromic acid. This would be the name in that particular molecule. Now, what about if I have those oxyacids? Okay, remember, I have my ites and my ates. So when I look at the polyatomic, if it ends in ate, I'm going to change the ending to ic. If my polyatomic ends in ite, I'm going to change my suffix to us, O-U-S. And then I write the word acid at the end of all the names. So if I end with ate, it's base name of oxyanion plus ic, acid. If I end with ite, it's base name of the oxyanion plus us, acid. So let's look at this. Let's just look at H2SO4. Remember, SO4, 2 minus, is sulfate. So I would use the base name, which actually happens to be sulfuric. So this would be sulfuric acid. If I have H2SO3, which is SO3 2 minus, which would be sulfite, this would be sulfurous acid. Here's some of those, that series where I have the hypo and the per. So if I had a hydrogen added to the first case, that would be hypobromous, right? So the ite goes to us, acid. Then I would have bromite, which is an ite, goes to us, acid. So that would be bromous acid. Here I have the ATE, goes to ic, bromic acid, and then I have the ATE also going to ic, which would be perbromic acid. So again, this takes some practice. These naming tools are critical because you have to be able to speak the language of chemistry, and naming things, I will give you in the future reactions that just have names, or we have to predict products and we know what elements combine, but we have to write the correct formula, otherwise nothing works. So I have to know how these molecules come together. I have to know how to name things. This nomenclature is a critical skill. That's why there's so much sort of work on this. There's a part of a lab that's all about nomenclature. So here, if we look at this, this would be binary because I only have hydrogen and I have sulfur. So this would be hydrosulfuric acid. This is going to be oxy acid because it's a polyatomic. The ClO3 minus anion is going to be chlorate. So this would be chloric acid. Notice if I do HCl, that would be hydrochloric acid because this is binary. That's why I have this hydro prefix in there. If I look at this guy, this is actually an oxy acid. This is a polyatomic ion, which is C2H3O2 minus. It's called acetate ion. So this would be acetic acid as the name. When the name adds an acid, what if I have the name and I need to write the formula? When the name ends an acid, I'm going to start with hydrogen. So I'm going to write the formula as if it is ionic, even though it's molecular. If I have the prefix hydro, I know it's a binary acid. If I have no prefix, it's going to be an oxy acid. If I'm an oxy acid and it's ic, my polyatomic is going to end, right? It's going to come from an ion that ended in an 8. And if it's an us, the polyatomic ion ended in the ite. So every hydrogen is H plus. Each hydrogen is a positively charged ion. So when I actually look at something, if I have SO4 2 minus, I need 2 pluses to balance that out. So my formula for sulfuric acid, which be H2SO4. Let's look at if I have HO3 minus, which is carbonate. This is -2. My formula, again, because it's -2, I need 2 H pluses. So this would go to H2CO3. 8 goes to ic. This would be carbonic acid. So do you get the idea? If I have, let's say, PO3, 3 minus. Well, if I write the acid for that, I'm going to have 3 hydrogen pluses to balance out that negative charge. This is called phosphite because it's got the one less oxygen than phosphate. So this would be H3PO3, and this would be called phosphorus acid. So just to practice, you first want to identify if it's molecular or ionic or an acid. Then you're going to use the different naming systems to go ahead and do that. So this is a metal with a non-metal polyatomic. I have potassium, and then the name of Cr2O7, 2 minus, is dichromate. This is also, so this is ionic. This has a metal and a non-metal. This is also going to be ionic. Both are representative elements. So I'm going to call this sodium nitride. This is molecular. Notice this is not a charge. This is not a nitrite ion. There's no ion charge. This is a molecular substance that has 1 atom of nitrogen and 2 atoms of oxygen. So it would be mono nitrogen dioxide, but I don't need the mono because the nitrogen is in the front because it's got the lower group number. It's group 5 instead of group 6. So this would be nitrogen dioxide. This is an acid. So I want to look at what polyatomic that is, right? That's an oxyanion. That's called a chromate ion. No, it's not. What is that guy? Chromate, no. Oh, that is chromate. Yeah, that's chromate. Never mind. I had a little brain fart there. So this would be chromate. Which goes to chromic acid. This sodium carbonate. I know I have an Na plus. My carbonate ion is CO3 2 minus. So I need 2 sodiums to every 1 carbonate. So I'm going to write Na2CO3. Sulfurous acid, that's going to come from sulfites. So I have a 2 negative, so I need 2 hydrogens. And then I'm going to use the sulfite anion, which has 3 oxygens instead of the sulfate, which has 4. So this is ionic. This is also an acid. This is ionic also, but it's got the transition metal. So I know from the Roman numeral 2 that I have an Fe2+. Phosphate is PO4 3-. So if I want to put them together, I would get Fe3 parentheses PO4 2. That subscript, or that subscript outside the parentheses says I have 2 phosphate ions. So hopefully you're getting the idea on how to use these systems in order to name these compounds. Kind of interestingly enough, this is sort of a top, an aside. Pollutants that can be emitted from various industries and automobiles and whatnot. So if I have these molecular compounds that can be emitted into the air by devices and things that form pollution, they go into the atmosphere. And when they're mixed with water up in the atmosphere, what they do is they turn into nitric and sulfuric acid, right? Those are very acidic compounds. So they turn into these acidic compounds, and then when the rain falls, I've got this dissolved acid in there, and that can fall or flow into lakes and streams, and that can raise the pH of the water, making it more acidic, and that can actually damage ecosystems and buildings and all kinds of other things as well. This is a great flow chart in your book. The first thing you have to do is determine whether the compound you want to name is ionic, molecular, or an acid. And then you're going to go through these decision trees and you're going to try to figure out the best way to name the compounds that you want to name based on this flow chart. That's the end of Module 4. So enjoy and have fun naming things. Good night.